Okay, so in this last video, I'm going to introduce kind of a few more advanced implementations of this try structure. And some of them will be a little bit more straightforward than others, but I want to give a chance to talk about other ways, different trade-offs you could have in your design, depending on your situation and kind of what you're optimizing for. So what we're going to talk about today is kind of, or in this video, is more advanced representations of this kind of next children array so that you can reduce the amount of space. So as a bit of a recap, what we're really focusing on in this structure is we're not changing too much about the nodes themselves quite yet. We're really just changing this data index care map I was talking about, like your children, and how you access a particular node based off what character you're looking at. And so right now we have a giant array here with one slot for every possible character, most of them being null if there's no children there. And we can traverse this tree kind of starting at the top and going down each node, finding the appropriate index for each character to know which node to jump to next. What we talked about in the last video a little bit was this seems like a huge waste of space. For example, if in this try with just two words in it, A and up, I have to use 1, 2, 3, 4 arrays, and each one of those arrays has 128 slots in it, because I just need that kind of, in the case that I want to add extra words, I need to have those slots available. And so you might already start to be thinking about, well, I'm really just trying to use this array to represent a map. So maybe I could just use one of our favorite map implementations instead of an array, mapping from character to node. And that's an exactly right idea. So for example, instead of using an array, what if we use a hash map? So make a hash map from character to node. And so now instead of having to store this 128 length array, we just let the hash table of whatever size it is, maybe starts with 10, maybe it'll resize. You just have a mapping from character to node. And then we could just look up efficiently still constant time lookup to look up kind of what node comes next. So it's the same idea as the array implementation, but it's trying to conserve space by using our map structure from before. This is entirely why it is so important in 373, why we stress this idea of abstract data types, ADTs. Whenever you hear like find a value based off some given key, the word map ADT should be screaming in your head. So if you kind of are trying to design your own more advanced structures like tries, it doesn't mean you have to throw out everything you're used to. Use the structures that we know in ways that they work well. You don't need that array that's really large. You don't need to implement resizing or how to find indices for particular things. You could just use a hash map that's already built in if that works for your situation. And so this hash-based try is a really great way of trying to save some memory while still getting that constant time. Now, we do have to remember that one minor downside to hash tables, because they want that constant time access, is they do have to use a little bit of extra memory, right? Because we want that hash table to be roomier. It's not as extreme as that 128 length array. It is a little bit extra. So if you are being a little bit more memory conscious, like you need a bit more safety in kind of how much memory you're using, maybe you're on a computer that's really, really small, then maybe what you can opt for instead is another implementation of our map ADT, like a tree map. So this will now get kind of meta here, because inside our try, there's a node for each character as part of our word. So my try has 4 nodes, kind of the empty string, the A, the U, and the P. We can represent the next children references as other nodes in a small binary search tree, just to figure out which child is next. So you can have in here, instead of using that hash map with the letters A and U for the next children, you can use a small binary search tree. And you can efficiently look up in that binary search tree with a little log operation, log here being in terms of the number of characters possible, 128. You could just search down this little tree to find the next available child. And this is a bit weird in some sense, to have like 2 sets of trees, one for the try itself, and these smaller trees inside to help you find the next child. And I agree, that representation's weird, or a little bit weird. So I'm going to throw something really wild at you. What if we combine them? what if we combine the tree for the try with the small binary search trees to help you find the next child, so that we can just really have one tree. We don't have to think about this relationship between two trees. So this enters kind of my third and weirder implementation, which is why I call the ternary search tree. This is actually a common data structure. The idea is this ternary search tree uses nodes to represent both the characters that we're using in our try, as well as the tree nodes to help us find the next child. Because if we look back at this kind of picture, we see that when I mentioned that there's these two distinct types of nodes going on, well, really these internal children pointing to the next child in the try really are storing the same type of information in some sense. So we can combine them into just one type of node. So here's the idea. Each node represents a character, right? Just like in our try, each node represents a character, and internally, each one inside one of those mini trees to help us find the next child, each node represented a character. So now we just combine both types of nodes into one character node. And that character node is going to have 3 children, not 2, 3. The left and the right children are to help you with this internal view of finding the next child. So this kind of internal mini tree of finding what child is next, that's what left and right is all about. So we treat kind of left and right as kind of like some sort of binary search tree to help you find the next child. But if you ever find a character that matches, we then go down. We have a third child, which is why we call ternary search tree. It has 3 children. The third child, the one in the middle, it doesn't really matter how you draw it, but we'll just say the one in the middle, that's kind of advancing you to the next try node. Instead of the next internal node to help you find the next child, it's the actual next node in the try. So this makes a little bit more sense with a more complete picture. But if we think back to our abstract try, we kind of had a node for each node in the try, each node from each character from the original string. And this was helpful because we can have this nice consistent mapping where the nodes at level 1 corresponded to characters at index 0. But now in this new implementation, we're kind of mixing things up. We're combining both the nodes in the try with nodes in a binary search tree to help us find the next child. And so now our tree gets a little lopsided, where the nodes that correspond to starting nodes might be all over the tree, because in some sense U became the start node, and then it kind of went down to the left to go to A, which is kind of its sibling in the abstract picture of the try. And so we kind of get this lopsided picture now. So to give you a little bit of practice with this, and I'll go through this in a second, I want you to try with everything I just said. We use this kind of one node to represent everything, left and right to help you search through binary search trees to find the next available try node, and going down is kind of like consuming a character to follow the next node in our abstract picture of a try. I have a picture of a ternary search tree, and I want you to tell me which node here is associated with the key CAC. So thinking about everything I just said, try this out, and then we'll go over this together. So take a minute, try this out on your own. Okay, so let's do this together. So this is this weird implementation of this ternary search tree where everything's combined into one tree. Notice, just like before, we still have our blue nodes to represent words in our try. So we have all of these words still here. So this is how this works with the ternary search tree. We start by searching for the letter C. So we start with the character A at the top of our try, and we say, oh, well, A is not C. And so this was not the start of some word that I actually cared about. And so now we need to go, because C is greater than A, we go down to the right. So now we're here. And now we see a match. And so we say, oh, well, since I found a match, the node I'm looking for is C, and I landed on a C, then I can kind of consume this character, I can consume the C, and move on to the A. And while I'm doing that, move down to the next node. Because whenever you find a match, you go down the middle child to go to the next step in the try, rather than going down left and right to find the next for the next node to help you find the next child in the try. And so now again, we find a match. We say, oh, I'm looking for an A, I'm at an A, so I'll consume that character and go down to the next node. So I'll consume this character and then go down to this character C. And now I say, oh, well, I'm looking for a C, but I'm currently at a G, so I need to go left because C is less than G. And so I go here to this next node, and now I find a match. And since I kind of consume the C, I found the match, and the C here is a key, it's blue, I know that I found this word. And so I could say that I found this word at node labeled 3. So kind of weird implementation, but it's kind of nice in some sense, in some simplification, to not have these like kind of nested trees. But maybe it's worse because it's kind of confusing because these trees are superimposed over each other in some sense. But this is a common implementation. It's nice because it's efficient in the sense that it doesn't use a bunch of extra space that's unnecessary, but it does have this downside that it is fairly more difficult to understand. It's a bit weird the first time you see this. I'm gonna go ahead and hide this penmanship right there. I want to go to talk a little bit about some wrap-up stuff. So first I want to talk about a little bit at a high level, how do you do this searching task now that you have this try? Exactly what I just did. Whenever you're searching in this ternary search tree, you always are going character by character, but it's a bit weird because sometimes you consume one of those characters you're searching for and other times you don't. So you're always starting at a node, and if you're looking for a character, if it's smaller, you take a left link. If it's greater, you take a right link. But if it's equal, that kind of like, oh, you found the character you're looking for, you can make the next step in the try. You go down, you take that middle link, and you move on to the next character to start searching for the next thing. You yield a search hit if the final node you land at yields a key that belongs in our set. So if you found one of those is key nodes. And it's a miss if you ever reach a null, or you ran out of characters to search for and you're at a non-key node. And I mentioned here that we get this kind of lopsided structure now because we kind of had this left, right, or middle structure in our tree, that we can actually kind of not have all the things at index 0 kind of at the same level, because sometimes going left or right is not actually advancing down the try. It's just about finding the right sibling to go down. So as kind of one last slide as kind of our final takeaway, tries are very useful structures for storing strings, or really, actually more broadly than that, any kind of structured sequential data. Now, its real-world performance is often much, much better than hash tables or search trees because it's actually really taking that string structure into account. And there are many, many different ways of implementing these tries. We talked about array-based ones, hash-based ones, and then this ternary search tree. And they work really, really well whenever you're looking for common prefixes. So this is just another tool to add to your tool belt. And you can use it in a lot of different applications outside of just autocomplete. The one very popular application of tries is in computational biology, where we're thinking about genomic sequences, DNA sequences, where there's lots of shared common patterns or common prefixes. And you could use a try to help build up kind of a common database, help you search for things that you labeled as genomes. There are lots and lots of applications of this stuff, and we're only scraping the iceberg. And I kind of like this as kind of like a final data structure to talk about because it is pretty niche. Like it's really only applicable with string data and other types of data, but it has its very particular niche. But it is this kind of nice wrap up of everything we've seen so far, being able to apply different ADTs or different data structures to solve parts of this problem that we didn't know how to solve at the beginning. And so I really like this as kind of like a culminating part of our course, as kind of really cool things you can do that have real impact on the world, right? Google has become a verb. When you want to search something, you Google it. And this kind of data structure was part of what powered what Google did. And they probably still use structures like this. They really do hide kind of a lot of what their search engine actually does. But they do use data structures like this to actually have real impact on the world. And so you can see how you can take the stuff that we've learned and actually have applications in lots and lots of important places. So with that, hopefully you learned something interesting about data structures today. And hopefully I'll see you in class where we can answer any questions about this because this stuff is really weird. So hopefully you enjoy this. I hope you learned something interesting.